So, last time we looked at the result which told us how to compute factorization of a prime ideal when you extend it to a bigger number field, and we will continue our study of local fields today. In particular, we will define a very important invariant called different. Okay. So, early on in the course I promised you the result that only finitely many primes in a number field ramify in a given extension, okay, and different is what will allow us to prove this. But before that, so let us recall some result that we proved very early on. Okay, so here is a fact. It is not needed to define different, but it is an important it's a important motivating fact, and I think we proved this early on. So, L over K be an extension of fields, be let me just say an extension of number fields, but this result is true for any finite extensions of field, be an extension of fields. Okay. Then any K linear map from L to K is of the form alpha going to trace from L to K of alpha times beta, okay, for a fixed beta. Okay, so if you fix a beta and take a map like this, it is clear that it is a K linear map, but the converse is also true. Okay, so any K linear map is of this form. So, you can ask a natural question, for what betas, for which betas in L it is true that so let me call this map phi sub beta. It's for which beta we have phi sub beta of OL is contained in OK. After all, these two are important lattices, one in L and one in K, and we can ask when does this linear map take one lattice into another lattice, into this second lattice, right. And so, we can define that as follows, but yeah. So, let S be equal to set of all beta in L such that phi beta of OL is contained in OK. And this is a subset of L a priori, but this subset has a very nice property. Okay. All right. So, what are we going to do first? Our big theorem is that S is a fractional ideal, is a non-zero fractional ideal So, this is our theorem today. In fact, S inverse is an ideal. So, in fact of OL. So, not only it is a fractional ideal, its inverse is actually an integral ideal. Okay. All right. So, how do we prove this? The proof will kind of take several steps. So, let alpha 1 up to alpha capital N be a Z basis of OL. Okay. So, remember that we have this is what we are interested in studying, but I am going to go all the way down to Q to study this, right. So, there exists beta 1 up to beta n in L such that trace from L to Q of alpha I beta j this is equal to 1 if I is equal to j and is 0 if I is not equal to j. So, this is called dual basis, right. Okay. So, why is this called dual basis? Well, it is a basis of the dual vector space if you like, but you identify the dual with itself because these are all finite dimensional things. Okay. So, what I can do is I can write beta I as summation j going from 1 to capital N C I j of alpha j for some C I j in Q. Okay. This C I j's of course need not be in Z. If C I j's are in Z, then beta I will be in O L, but we are not guaranteed to have dual basis inside O L. Alpha i's are in O L, but that does not mean that beta i's are also in O L. Okay. So, what we have if you rewrite this the duality between them. So, we have trace of alpha I alpha j times C j times I think, yeah, if you take these two matrices you get that this is equal to identity. But now remember, what is this? This thing, determinant of trace alpha I alpha j, this gives dk, the discriminant. Right. Therefore, discriminant times C I j is in Z for all i's and j's, right. So, that is a very nice thing. So, although these C I j's are in general rational numbers, what we know about them is that their denominators are no worse than the discriminant. Hence, what we have is that S, this S that we had before, this set S recall that we had before, right, is actually, so this S is contained in the OL module generated by betas, which itself is contained inside dk inverse of OL, right. So, hence S is a fractional ideal. Okay. And it is non-zero because 1 is in it, right. S is non-zero as 1 belongs to S. Well, not just 1, why just 1? We have OL is contained in S. So, in fact, right, therefore, S inverse is contained in OL inverse, which is just OL of course, right. So, S inverse is an integral ideal. So, we have proved the theorem and we can make the definition. So, different of L over K denoted as this d L over, this is supposed to be my script d, this is S inverse. Okay. So, it is an ideal inside this, right. And if you take, so here is a proposition slash exercise, we kind of have this from whatever we have done up to now. So, if you take norm from L to Q of this different, this is equal by what we have shown before, this is equal to mod of dk. right. So, it is modulus of the discriminant. So, that is a wonderful new invariant that we have defined. It is called the different or the different ideal. It is an ideal, right, it is not a number. So, how do the what happens when you change the field? So, let M over L over K be extensions of number fields then if you take the different from the largest field to the smallest field, this is product of different from the largest field to the intermediate field L, and then product of L over K, right. Now, again I want to kind of point out the subtlety in this, right. So, this thing is an ideal in OL. So, it is in the smaller field, whereas these two are ideals in OM. So, what this means is that you are first extending the ideal to OM and then taking the product, but that is same as taking the product of these two ideals inside OM. Okay. So, these two sets inside OM. So, we do not write OM different of L over K because it is the same kind of product, right. OM times this first thing will be the different of L over M over L, sorry. Okay. Now, you will realize when you work with different for long enough, it is always easier to work in terms of different inverse because that has an explicit definition, right. Different does not have a very explicit definition. So, if you take alpha in different of M over K inverse, this is same as saying trace from M to K of alpha beta is in OK for all beta, right. But this is same as saying that trace from M to K of alpha beta lambda is equal to trace from M to not M, I want to take trace from L to K of something that I have already taken trace of. So, this is lambda trace from M to L of alpha beta belongs to OK for all. So, this was for all beta in OM, this is for all beta in OM and all lambda inside OL, right. Because if I multiply this beta by lambda in the left hand side I am not changing anything. So, this is same as saying trace from M to L of alpha beta, this is in the right. Now, I have some condition on all lambda, which means that trace of alpha beta. So, this second trace on the right trace from M to L of alpha beta, this is the term that appears on the right hand side. This is in the inverse different, right. So, this is in L over K inverse for all beta in OM, but this thing is same as saying that gamma times trace M over L of alpha beta is equal to trace from M over L of gamma alpha beta belongs to OL, not OL, yeah, OL for all beta in OM and all gamma in delta, sorry, this d L over k, yeah, I mean because I want the trace to be in the inverse. So, this is same as saying that alpha gamma belongs to trace sorry, this different from M to L inverse for all gamma. This is same as saying alpha belongs to different M over L inverse, different L over K inverse, because I am taking gamma inverse there, right. So, that is that proves the lemma. So, there are lots of if and only if things, otherwise you would have to take lots of cases, and I do not really want to do that. So, different behaves well in a tower of number fields, that is what this is saying. Okay. All right. So, now analogously we can, so that finishes proof of this lemma, by the way. Right. So, we can also define local different So, what I have is LP over KP, and I can consider, right. So, any linear map from LP to KP is of the form trace is again of the form. So, let me, so any linear map LP to KP is of the form phi sub beta from LP to KP, and what is this map? Alpha goes to phi beta of alpha, which is trace from LP to KP of alpha beta, right. So, again we can define S to be set of all betas in LP such that phi beta of OP is contained in O small p, right. Again we can show, so take this as an exercise because it is a repeat of the first exercise. We can show that S inverse is contained in O sub capital P is an ideal. Okay. All right. So, so S inverse you denote this by LP over KP. So, this is local different. All right. So, that is the definition of local different, and now there better be some yeah. So, what happens now, here is a subtle point. So, this means that LP over KP, this is equal to P to some power. Let me denote it by A1 for some A1 bigger than or equal to 0. Okay, it may happen of course that different is same as O sub capital P. So, A is in that, yeah, I do not know why I wrote 1 there. Yeah. So, it can happen that A is 0. Okay. All right. So, lemma let L over K be an extension of number fields this is a, it is a nice lemma, but it is kind of subtle. So, let us spend some time on this. Then if I take different from L to K, this is product over all primes of capital L, different from LP to K sub P. Okay. Now, the subtlety is the following, right. We define different as an ideal in O sub capital P. So, it looks like these things on the right hand side, they are ideals inside inside the completion, whereas the left hand side is an ideal inside OL. So, what does this mean, right? So, this should be interpreted as P to the power A is the largest power of P dividing the different if and only if different from LP to K sub P is equal to P to the A, right. So, that is how it should be interpreted, that order of any prime dividing the right hand side, the left hand side is same as the order dividing the left hand side, although they are in two different rings. But this is a very nice way, the way this product formula is written, it is a very nice way of writing it and remembering it, that the global different is product of the local different. Okay. But this kind of should be taken to understand this what this means. Okay. So, it is this way. Alright. So, because it is kind of an awkward statement, the proof will also be a somewhat awkward, right. It is kind of, you have to interpret things correctly whatever I write. So, here is an exercise that you should do before doing this exercise. Any alpha in L, or maybe let me write this is eta in L, can be written as eta is equal to alpha minus alpha prime for alpha prime in L such that L is k alpha and it is also equal to k alpha prime. So, any element of L can be written as difference of two generators, right. So, that is what this is saying, and this is kind of it seems very difficult at first, but it is not if you get the right idea, and I leave that as an exercise. So, if L is k alpha, then using the fact that L tensored Kp is direct sum I going from 1 to R of L Pi if POL is equal to P1 to the E1, PR to the ER. We proved this 2 lectures ago. So, using this fact we get that trace from L to K of alpha is equal to summation over I going from 1 to R trace from LPI to KP of alpha, right. And then using the exercise, and because and as trace is additive, trace from L to K of alpha is equal to summation I going from 1 to R trace from LPI to KPI KP, there is no I there, of alpha for all alpha in L, right. It does not matter whether alpha generates K or not. Okay. So, now we have related local traces to global traces, right. So, that is a good starting point because different is defined in terms of traces. Okay. So, if beta in K is also in different, sorry not K, if beta in L is also in different from LP over K, LPI over KPI inverse for all i's, for all I, and alpha belongs to OL, then we know that trace from LPI to Kp of alpha beta, this is in O P for all i's, right, because alpha is in OL, it is also in O capital P I, and by the definition of what different inverse means, we have this, right. So, hence beta is integral at every prime of L, not dividing let me try that again. So, my claim is that the local different divides the global different. Okay. So, let me remove this part and let me say the following. Okay. So, now my claim is, I don't think we will be able to finish this today. So, my claim is that product LP over KP, this divides DL over K, but this is same as saying product I going from 1 to R DLPI over KP divides DLK for all P, right. So, this is same as saying that, so when does 1 prime divide, when does a so if A divides B, if the ideal A divides ideal B, this means that DL over K inverse is contained in product DLPI over KP inverse, right. So, we want to show this, right. So, I think this will take some time. So, we will postpone the proof of this and the reverse inclusion to next time. So what we have defined, what we have done today is we defined global different, local different, and we are in the proof to show that global different is a product of local difference. So, we will finish this proof next time and we will see how to find different using some explicit algorithm. We will find local difference, and then using this result that we are proving now we will find global different.